All right, so today we are going to talk about, well, not that yet, more modeling and functions. So this is chapter 2.4 in your textbook. It's primarily review. There are a couple of new things that we're going to talk about, but for the most part, it's pretty similar to stuff we've already been doing. So hopefully this won't be too long or too terribly difficult. So the first thing, linear models. Linear models are basically just linear equations that define real-world relationships. So the things like a car traveling at a constant speed or something falling, oh, that's got a constant acceleration, so it'd be slightly different. But there are a few different um, functions that this represents in the real world pretty well. We'll talk about a couple examples in a minute. The function is still written as f of x equals mx plus b, but in this case, m and b represent very specific real-world values. Generally, m represents a constant rate of change, and b represents an initial value. So if we look at college tuition as an example, in 2015, the average cost of attending a public college was $9,400 and was projected to increase by $300 every year until 2018. So we can model this pretty easily as f of x equals 300x plus 9,400. Now, earlier we talked about doing, this is slope-intercept form. Earlier we talked about doing slope-point form. And you could do this as slope-point form, and what you'll notice is that it would end up being the same 300 and then be x minus 2015 plus 9,400. So that might make you think that, oh, I should probably use a value different, right? Because if you simplify this out, you're going to get some really wonky thing. But this is very specifically for these specific years. So your x value would be the number of years from 2015. So 2016 would be an x of 1. 2017 would be an x of 2, 2018 would be an x of 3. So it's a little bit different in what it's actually trying to tell you, but it makes more sense for the actual real world function we're looking at. So if we had written this value in 2015 and we said in 5 years, what's the cost going to be? We can just plug in 5 for x instead of having to worry about doing the year and doing more complicated calculations. So it kind of just skips this step right here of this x minus 2015. And you'll see that that's kind of the case in some of these, and it's not necessarily the case in other ones. So things with dates, it's usually going to be the case. But as long as you understand that you're going from the initial value, then you shouldn't have any issues. So this does lead us into a discussion of what are called piecewise functions. And piecewise functions are something that are probably pretty new. You might have seen them once or twice before, but you probably haven't done a whole lot with them. And we're not going to do a ton, but we are going to look at a little bit at what they mean, how they're written, and what they actually describe. So sometimes it makes sense to write a function in various parts. The example we're going to look at today, which is also the example your textbook uses, is the Fujita scale, which classifies the intensity of tornadoes on a scale of 1 to 5 based on wind speeds. And it results in what we call a piecewise function. So this is what that looks like. These are the values that get assigned to whatever the tornado is, the intensity from 1 to 5, and then these are the wind speeds. So this is the minimum wind speed to be a class 1. This is the minimum. 72 is the maximum to be a class 1. It has to be more than 72 to be an intensity of 2 and less than or equal to 112. So you guys can hopefully see how this works, the basic idea at least. 1 is from 40 to 72, 2 is from 72 to 112, 3 is from 112 to 157, 4 is 157 to 206, and 5 is from 206 to 260. The interesting part about something like this is what the graph looks like. So in this case, the graph of the Fujita scale, and I'm sorry that it's so blocky and gross, but it looks like this. So you've got kind of a direct thing here, and then you've got this big jump, and then you've got another one here, and then you got a big jump, and then another one here, and a big jump, and another one there. So if you ever see something like this, you'll know that it's a piecewise function. Piecewise functions can be continuous or they can be discontinuous. So if it's continuous, it might look something like this, right? And then it might go whoop, whoop, whoop. But it's still touching at every point, but these would obviously be different formulas, right? each of these curves going the opposite way. But in this case, it's a little bit simpler than that. It's just straight lines across, and it's discontinuous. And we'll talk more about that in a future chapter, I believe. But for right now, so this is something you might actually see in a homework problem or on your test. This is a really simple piecewise function. There's only two parts, but you'll notice that it actually uses x values over here instead of just saying that f of x is equal to a number. Graphing these would be a little bit more difficult. We're going to go ahead and practice them in a second. But we can answer all of these questions just by being given this function right here. So first of all, let's start with what is the domain of f of x. So the domain of f of x has to be x values between what we see here. So we see that our minimum x value possible is -4. It is continuous, at least on the x axis. So it is continuous from -4 to +4. So our domain is, these are both equal to, so we're going to use square brackets, -4 to 4. Now, if for some reason this piecewise function was from -4 less than or equal to x less than 1, and then we jump to 2, you would have to say, and then we did this, x. So see how these aren't continuous. If you have an x value of 1.5, it doesn't fit into either of these categories. So this would be non-continuous on its domain, which is the x values. And then we would, if it was non-continuous like this, if we had this jump from 1 to 2 here, you would have to write the domain like this. So you have -4 to 1, and then 1 is not included because it's a less than sign. And then you'd have to add in the, well, it's a union symbol, the 2 to 4. So the graph would be very different if we made it look like this. But anyway, so in our current one, since it's continuous, we've got -4 to 2 and then 2 to 4. We get this. It is -4 to 4, and both are included. So next up, we'd want to evaluate the f of -3, f of 2, f of 4, and f of 5. So for f of -3, first we have to look, where is -3 on these values? -3 is between -4 and 2, so we're going to use our first function, and -3 minus 1, so this would be our x, and that equals -4. So f of -3 is equal to -4. F of 2, now you see 2 is in both of these, but because this one's less than, 2 does not fit into this equation. 2 only fits into this equation. This is the less than or equal to sign here. So in this case, -2x, so -2 f of 2 equals -2 times 2, because that's our x value, equals -4 as well. Interestingly, these both came out the same. And then the next one, we want to evaluate f of 4. So f of 4 is also in this bottom function, so we're going to use the f of x equals -2x. So f of 4 equals -2 times 4, which is equal to -8. And then the last one, f of 5. Now, f of 5 is not in either of these two functions, right? F of 5 is not between -4 and 2, and f of 5, or 5 is not between 2 and 4. So for 5, f of 5 is actually undefined, right? There's nothing in our function that tells us what to do with an f of 5. If we have an x value of 5, it doesn't fit onto either of these, so we call it undefined. And that's how you'd write an answer for this too. So now, sketching a graph of f of x, this one, can't really use an eraser right now. So let's do, here, I'll rewrite these really quick. F of -3 equals -4, f of 2 equals -4, f of 4 equals -8, f of 5 undefined. Okay, so for sketching the graph of f of x, or something like this. Then from -4, so we know that -4 is going to be my lowest x value. +4 is going to be my highest. So let's put in -2 and 2. -2, -4. And then I don't actually know what my highest x is going to be. Looks like it's going to be 1, actually. But let's say we want to go 5, 10, -5, -10. Okay. So now if I'm going to graph this, I want to first make a chart of values. It's going to be the easiest way to do this. So we want to do f of x and x. And now I'm actually going to break this into 2 parts. So this is going to be f of x for the top function. So f, I'll say 1 of x. And then I'm going to make another one that is f2 of x, and that's going to be for my bottom function. So for this one, the minimum value is 2, maximum value is 4. We'll add 3 in the middle because that just makes sense. For 2, we're going to get -4. 3, we're going to get -6. And 4, we're going to get -8 for that bottom function. Now, the values that you choose on this one are a little bit tougher. I'm going to do -4. I'm going to do -2. I'm going to do 0. And then I'm actually going to do 2. Now, f1 of x can't actually be equal to 2, but 2 is the absolute last point on this function. We're going to find this point as it would be on this function, but since it's less than, we're just going to have it not filled in instead of filling it in with a bubble, which we're going to do for the 2 over here. For this top one, we're going to use the non-filled in bubble. We still need that point, though, because that tells us where this graph ends, this x minus 1 part. So x minus 1, we're going to get -5, we're going to get -3, we're going to get -1, and we're going to get 1. So 2, 1, that's somewhere like right here. 0, -1, that's like here. -2, -3, that's maybe there. -4, -5, that's there. So then we've got a line going like this. And then at 2, we're dropping to -4, so maybe right there. And then we go 3, -6, and 4, -8. So it should look something like that. That's going to be the basic look of your graph. And obviously, if you have graph paper and stuff, it'll look a little bit nicer than that one would. But that is okay. Now, this is a discontinuous function in terms of its range, right? The y value is not connected, so it's not completely continuous. It does have this disjointed bit in the middle. But every single point of x from -4 to +4 exists somewhere on this function, right? There's no point that we can't get a single input and output to from -4 to 4. Anything on the other sides of those, so anything greater than 4 and anything less than -4, we won't get a value for, but anything between -4 and 4, we will. So when it asks, is it continuous on its domain, specifically, it's asking whether or not all of the x values possible between its smallest and greatest point actually have some kind of f of x value. And in this case, they do. 2 is the only one that might confuse you on this, this break right here. If this right here wasn't an equals to, just a less than, and this was an open point as well, it would not be continuous because there's no value for f of 2. But since we have one of them as an equal to and one of them as a less than without the equal to, it is continuous from -4 to 4. So this one, yes, it is continuous. So the next thing we want to talk about is called the greatest integer function. And this is actually super, super easy. It's going to seem a little bit more complicated than it actually is. But it's a common piecewise function, and it's called the greatest integer function, which is written as f of x equals this weirdly bracketed x. I think technically these are supposed to be combined, but I don't know how to draw that on my computer. And it doesn't really matter. If you see this kind of double bracketed x, that is the greatest integer function. And what it means is that this double bracketed x is equal to the greatest integer less than or equal to x. So if we look at some examples, the double bracketed 2.3 is equal to 2, right? 2 is the smallest integer that is smaller than, or the largest integer that is smaller than 2.3. 3.14, so I chose pi just for fun, goes to 3. 5, since 5 is an integer, it is the greatest integer that is less than or equal to 5, so 5. and then negative 3.4, because it's negative, you would go down to negative 4. So if you just like think of these somewhere on a number line, go left until you find the next integer. It's not too terribly hard. But this function is often used when fractions must be ignored, such as being charged for mileage when renting a truck. Now, obviously, all of you were too young to have rented a car before. In fact, honestly, until 2 years ago, I was too young to have rented a car before, and I've never done it. But they often charge mileage. So, like maybe they charge 10 cents per mile. So it'd be abbreviated like this: 0.10x. But let's say you drive 1.7 miles, they don't care about the 0.7, so they would just call it 1. So that's what this greatest integer function allows us to do. If we take, it just rounds down, basically. So hopefully that one's not too terribly difficult. And your calculator can do this function using the int x button. So I used this once when I was making a guessing game, because I had to generate a random decimal and then I rounded that to a whole number so that I could have people try to guess it. But other than that, I don't think I've ever used it in an actual math class. So generally, you're not going to need to graph this function. But if you did, then it would be a piecewise function that looks basically like this for each integer. So each one of these is going one whole spot, and then it's going up one each time. And it would do this infinitely, both in the positive and the negative direction. So it's kind of a cool little function, but not necessarily the most useful. The last thing we're going to talk about is direct variation. Honestly, you can think of this as any linear equation without a b. So when b equals 0. So when a change in one quantity causes a proportional change in another quantity, the two quantities are said to be directly proportional. They might also be said to vary directly. The wording in your textbook gets a little bit funny, but basically, if it says that they are directly something to each other, proportional or varying or whatever, that means that they're just a proportional relationship. So the example is if you get paid $10 per hour, the amount you are paid y is equal to 10 times the number of hours worked x. So in this case, y equals 10x. And 10 is your k. So that is, okay, I don't know why that random line was animated and the rest weren't. If x and y are directly proportional, then y equals kx, where k is the constant of variation. So this k is just some number value. It's the proportional relationship, basically. So in this case, we have y equals 10x because we're making $10 per hour. Total amount of money made is equal to 10 times the number of hours worked. So 10 is our constant, our k value here. So if we know that x and y are directly proportional and we know one set of corresponding values, we can solve for the constant here. For example, if we know that somebody made $57.75 working for 7 hours, we can solve for their hourly rate. And you can probably do this just conceptually. You probably really don't need me to tell you how to do this, but you just divide both sides by 7, right? Divide by 7, divide by 7, and then you're going to get that your k is equal to 8.25. So the person makes $8.25 an hour. I'd get a new job if I were them, but whatever. Especially if they're in Oregon. Minimum wage is like $11 now. So then we can rewrite this function as y equals 8.25x. So if we use a direct variation example, this is also directly from your textbook. I think this might actually even be one of your homework problems. I don't remember. But it says let t vary directly with x. T equals 33 when x equals 5. Find t when x equals 31. So in order to do this, we know that y equals k. Oh, whoops, hold on. Let's do t since they're using t. Oh, oh no. Hold on, sorry. Just a second. Okay, let's try that again. So in this case, t equals kx. So when t is 33, so 33 equals k times 5. So we divide both sides by 5. And we get that k equals 33 over 5. So then we plug k into this. We now have the equation t equals 33 over 5x. And then we want to solve for when t is equal, or when x is equal to 31. So we're going to have t equals 33 over 5 times 31. And when you solve that out, let me use a calculator really quick because it's a gross number. 31 times 33, we get 1023 over 5, or if we want to simplify that, we'd get 204 and 3/5 equals t. Sorry. So that's how you'd solve a direct variation problem. Like I said, they're really just super easy y equals mx plus b problems. This is a pretty basic algebra step right here. So hopefully you guys know how to do this without too much trouble. And that's actually all we're doing for today. So this assignment is somewhat longer, but the way this week is going to work, and I'll talk about it more in class after you watch this video, is Monday and Tuesday, you're going to have new lectures with new assignments. And then Wednesday and Thursday are going to be catch up, get help, get work done, get ready, and study for your test days. So there will be no new material Wednesday or Thursday. And then Friday, we're going to have the quiz over this unit, which I think will hopefully be easier than the first quiz. This covered a lot more like similar information. Tomorrow, we're going to go over one new thing that I think is a little tough, but it shouldn't be too terrible for you guys. So we will hopefully get around to that and get you through it, get you ready for your quiz on Friday. But that is all for this video.